If you recall, last week we were working on integration by substitution, which is the anti-chain rule. We talked about what we need to make substitution happen. We need something that we can identify as an inside function. Then we need to identify the outside function that we're actually going to be integrating. And then we need to make sure that the substitution is going to work based on what we have. We have to make sure that there's something left over to be the dw, because we're trading our x integral for a w integral. Sometimes it's clear the substitution that we need to make because there's an obvious inside function. The question is, will that substitution be appropriate for the problem? Do we have something for the dw, and do we have an answer for all the x's that have to be converted to w? So let's take a look at these two problems. They're very similar. They're similar in that I have the same inside and the same outside function, but in one I've got an x to the fifth, and the other one I've got an x to the fourth. So in both cases, we're going to say the inside, which we've been calling w, is x cubed plus 1. Note that in both of these integrals, our first thought for substitution should be the x cubed plus 1. In both cases, we have the same outside function. Both of these functions are square roots of w. So in both cases, we have the same outside function. Square root of w. Now we have to make sure that we have the parts to make this substitution go. To make a substitution of x cubed plus 1 work, I need to have a constant multiple of dw. And in this case, dw is 3x squared dx. Well, in both cases, dw is 3x squared dx. So in both cases, I need two factors of x to be the dw. In particular, x squared dx is going to be a 1/3 dw. So in both cases, x squared dx, that's the piece that I actually have, and I'm just going to move out the 1/3 dw. So in both cases, I need two factors of x to be the 1/3 dw. But in the first problem, we'll have 3 x's left over, and in the second problem, we have 2 x's left over. So in the first problem, we're going to read this x to the fifth as an x to the third that we're not dealing with, and then an x squared. Then we have the square roots of x cubed plus 1. And then the dx is going to pair with the x squared to be the dw. On the other problem, we'll use the same technique. But we're splitting an x to the fourth. So there's an x squared times x squared. Now I'm setting aside this second x squared to be the dw. And I have the square roots of x cubed plus 1. And then the dx is going to pair with the x squared to be the dw. In both cases, I have some x's left over. On the left, I have an x cubed left over. On the right, we have an x squared left over. On the left, x cubed is easy to replace. So here, I can replace this x cubed with w minus 1? It's because my substitution for w can be easily turned around into an x cubed. So I can replace that x cubed with a w minus 1. The problem is, on the right, I have an x. It's easy to solve for x cubed, but we don't have that. We have x squared. Because the relationship between w and x is a cube, it's really hard to get at x if x when x is squared. So even though we can we can solve for x cubed, that doesn't help us with the x squared. Being able to write x cubed as w minus 1 doesn't help us because we need to replace an x squared. So this means we could write x squared as w minus 1 to the 2/3 power, and that's just causing more problems. I still have 2 terms inside of a radical. So even though I've replaced my square root of 2 terms, I've introduced a cube root of 2 terms. So I can solve this for x, solve x cubed equals w minus 1 for x. And then raise both sides to the 2nd power. And that's not helping us. Over on the left, this x cubed is going to be replaced with a w minus 1. So I have a square, an integral. X cubed is the w minus 1. X squared times dx gets replaced with 1/3 and dw. The square root is just the square root. And x cubed plus 1 is replaced with w. The benefit is I've got one radical, the square root of w, and I can distribute it to the w minus 1. Now I can write this as powers of w. So I have a 1/3 integral of w to the 1st times w to the 1/2 is w to the 3/2. 1 times w to the 1/2 is w to the 1/2. That substitution has worked. I got a dw integral. That was better than what I started. Over on the right side, we see that replacing x squared with w minus 1 to the 2/3 just messes everything up. We can still make the substitution where x squared is w minus 1 to the 2/3. The square root, the x squared and the dx both combine to make a 1/3 dw. That still works. And the square root of x cubed plus 1 can be written as the square root of w. What we wanted to happen, what we needed to happen from this process is being able to write the square root of x cubed plus 1 as something to the 1/2 power that we can distribute. The problem is I've got w minus 1 to the 2/3 power. I've still got a radical with 2 terms in it. And that means the substitution didn't work. We still have a radical with 2 terms. We still cannot proceed by just distributing the square root of w. Now, it wouldn't be a problem if we had w minus 1 to the 2/3 and that was it. The problem is that we have the square root of w and the w minus 1 to the 2/3. So if we just had w minus 1, a linear factor being raised to this funky 2/3 power, that's fine. We just add 1 to the exponent, divide by the new exponent. The inside is linear. But if we write this as one radical, the square root of w outside has to get distributed in to the 2/3. I'd have to raise the w to the 1/2 to the 2/3 and put it in with these w's, and it's no longer linear inside. So there's nothing we can do at this point. We went from having 2 terms in a radical to having 2 terms in a different radical, and that didn't help. On the left, the reason that it worked was we started off with 2 terms in a radical and got down to 1 term in a radical and a polynomial. And that we can multiply out. So having 2 terms inside of a radical without something to substitute on the outside, that's the problem. So if you happen to finish these, I should finish this problem. So I still have this 1/3 on the outside. Integrating w to the 3/2, we add 1 to the exponents and divide by the new exponents. With w to the 1/2, we add 1 to the exponents and divide by the new exponents. Now I need to replace my w with x cubed plus 1 and then multiply by 1/3. So I'll have 2/15 x cubed plus 1 to the 5/2 minus 2/9 x cubed minus 1 to the 3/2 plus some constant. Over on the right, we still have that w minus 1. We have 2 terms inside of a radical. That's what we were trying to avoid in the first place. Over here on the left, that w minus 1 was to the 1st power. Over here on the right, the w minus 1 ended up being to the 2/3 power.
Hey, Professor, could you talk about how you got 3/2 and 1/2?
Yeah, so I take the relationship w equals x cubed plus 1. If I solve that for x, I need to subtract 1 from both sides and then do a 1/3 power. That's a cube root. So x by itself is w minus 1 to the 1/3 power. Then if I want to figure out what x squared is equal to, I can just square both sides. So x squared is just x squared. When we raise w minus 1 to the 1/3 power and to the 2nd power, we get w minus 1 to the 2/3 power. So it started off with w is equal to x cubed plus 1. If we want to solve for x, we'll subtract 1 from both sides. We'll raise both sides to the 1/3 power. That's the same as a cube root. Then if I want to know what x squared is, because that's what I have in the problem, I can square both sides. X becomes x squared. And if I raise w minus 1 to the 1/3 power to the 2nd power, that's going to be w minus 1 to the 2/3 power. Unless the question was over here on the left, this 2/3, when we integrate something, we have w to the 1/2 power. So we add 1 to the exponent and divide by the new exponent. The integral of x to the n dx is 1 over n plus 1 times x to the n plus 1 plus c. Add 1 to the exponents, divide by the new exponent. So the integral of w to the 1/2 power dw is going to be w to the 1/2 plus 1 divided by 1/2 plus 1. 1/2 plus 1 is 3/2, and 1 over 3/2 is 2/3. So the reciprocal of 3/2 is 2/3. So the challenge in this substitution game is knowing how substitution is supposed to work, knowing what we need to make substitution work. We start by deciding what we want to substitute, and then we have to make sure that we can have all the parts that we need to make that substitution work. On the left, because we had x to the 5th, I could break that up to an x cubed, which easily turned into an x or into w, and the x squared, which we needed to make the dw. Over on the right, we had enough x squared to be the dw, but that left us with an x squared that we could not convert to w conveniently. We could literally, but we couldn't conveniently. So it didn't get us to a place where it was useful to have that integral in w. The integral in w was just as bad as the integral in x. Any other questions? One of the goals is to get your substitution skill to the point that you don't have to write down what you're substituting. You can just think what the substitution should be and know what other pieces you need to make the substitution go. So the baseline version of this problem with this x cubed plus 1 if I said I want them to integrate a square root, but it's not going to be a square root of x, it's going to be the square root of an x cubed plus 1. So if I want you to use substitution, I have to think if I want them to make the inside x cubed, then I need the dw, which is going to be 3x squared. So I have to put at least an x squared out here. The rest of it, what you want to be able to see is I'm going to make w as x cubed plus 1. So this is going to be a square root of w. That's what we're integrating, the square root of w. The dw is going to be 3x squared, and I have that over here. So I already know that the derivative of the inside is 3x squared. So that's going to, but I only have x squared. That's going to produce a 1/3. That's going to produce a 1/3. And then my integral, this is the square root of w. We're going to add w to the 1/2. So we're going to add 1 to the exponent and multiply or divide by the new exponent, which is going to be 2/3. The square root is going to be x cubed plus 1. X cubed plus 1 is my inside function. To the 3/2. And then all you have to do is write that as 2/9. The goal is to just write down 2/9 x cubed plus 1 to the 3/2 and have the rest of it take place just by observation. That is what we're aiming for. That is probably not where it's going to start. But the part where we're thinking, where we write down W is x cubed plus 1, so that y is the square root of W. And the dW is 3x squared into x. We want to see where that 1/3 came from. We want to see where the 2/3 came from. And all this is taking place just by thinking about it. Even this part right here, we're thinking about it. So the only written work that you have is the antiderivative. Because in this nice straightforward one, you want to see what the inside is. You want to see the x cubed as the inside. You want to see that x squared is only being there to be the dW. Any questions? This kind of thinking is what takes substitution from a method that we can understand and generalize to just doing the problems in the book. We want to understand how substitution works. And since it's a mechanical thing, we get a lot of that understanding by doing lots of problems. All right, so that's substitution. And previously, and I mentioned that substitution is the anti-chain rule. And I also said that all of our derivative things are becoming integral things or antiderivative things. We're just turning them around. So substitution is a process by which we reverse or inverse, find the inverse of the chain rule. So we have to go on to the next one, which is integration by parts, which is the anti-product rule. So integration by parts is the anti-product rule. Now, remember, we're not learning integration by substitution and integration by parts because these are things that we're going to be doing all the time. It's still a skill that we want to have. If you drive a car on a regular basis, you should know how to parallel park. And I'll just pick something else at random. You should know how to drive a manual transmission. Whether you're practiced or not is one thing, but you should know the concept of how the clutch gets involved with the gas pedal and the gear lever. You should know the process. It's going to be different when you get into different cars, but you should know the process so that you can work out what's going on. However, you can live your entire life in just automatic transmissions and no parallel parking whatsoever. You say, I'm just going to avoid parallel parking. You could live your life and never have to parallel park. And yet there it is, still on the driving test. Because if you have those two skills, even though you don't need those two skills, If you have those two skills, you are a better driver. You have improved what you can do with driving. In the same way, understanding integration by substitution and integration by parts, you can live your whole life. In fact, after you get out of Calc 2, because we do this again in Calc 2, after you get out of Calc 2, I can pretty much promise you, you won't have to do substitution in parts ever again. You'll be done. But that's not the point. That was never the point. Maybe it was the point at some time. But it has not been the point as long as I've been alive, or been alive and doing math. But you're a better mathematician if you have these tools available to you, regardless of whether you're going to use them or not. It would be really cool if I knew how to use a slide rule, but I don't. And everybody said, well, we're just going to use calculators anyway. And once again, it was people in the teaching profession saying, you don't need to know a thing. All right. Let's talk about integration by parts. Here's the good news about integration by parts. There's a formula for it. Here's the bad news about integration by parts. There's a formula for it. Let's dispense with all why this is the anti-product rule, and we'll just use proof by authority. This is the anti-product rule. That's where this comes from. And when students are like, well, yeah, but why? I'll be like, oh, quiet you, just trust me. So the integration by parts, this is the way that I remember it. It's the integral of u dv equals uv minus the integral of v du. There's two parts that you're given. The given parts are u and dv. The parts that you have to find are du and v. So over here in the u dv, these are the given parts. This is integration by parts. U and dv are the given parts. The parts that you have to find are the v and the du. So the v and the du are the parts that you find. Then you just put it all together in the formula, uv minus the integral of v du, and integrate the v du part. So part one, choose your given parts. Part two, find the parts you find. Part three, plug into the formula. Part four, evaluate your secondary integral. Part five, since I didn't want 4 parts, repeat if necessary. I usually refer to this integral of v times du as the secondary integral. This is not a standard term for this piece of the integration by parts. This is just what I call it. Let's take a look at an example of integration by parts. Let's suppose I wanted the integral of x times sine of x dx. The first step in using integration by parts is making sure that you're not looking at a substitution problem. So we look at x times sine of x. There's not really an inside problem or an inside function. This doesn't look like the composition of functions. This looks like a product of functions. So step 0, this is not substitution. So the first step in doing parts is making sure that you're deciding to not use substitution. Substitution is like the default. It's the first thing that you look for. And in this case, no substitution available. If w equals x, then dw is dx, and I'm just writing my x instead of a v on top of an upside down v, just two v's next to each other. So it doesn't help. So that means we're gonna, since it's not substitution, we're going to use parts. The two parts are x and sine x. So I'm going to call one of the parts u and the other part dv. So let's say u is equal to x and dv is sine x dx. The dx should always be along with the dv part. Eventually, we're just going to forget the dx is there and make it sure it shows up in the right places. But we start off by deciding which is u and which is dv. This raises a question. How are we supposed to know which one is which? And the answer is do a few more problems and you will just know. So step 1. Break up your given parts into a u and a dv. Next, we need to find our found parts, the v and the du. So to find du, just take the derivative of u. The derivative of x is 1 dx. So du is just dx. We differentiate u to find du. We also need to find v. Since we know what dv is, the derivative of v, we integrate to figure out v. So v is the antiderivative of sine, which is minus cosine. Now I have all 4 parts. So step 2, find du and v. Now you have the parts you need. So it's time to put the 4 parts into the integration by parts formula, uv minus the integral of v times du. So the integral of u times v is uv So x times minus cosine x minus the integral of v times du. It's negative, so I'm going to put negative cosine x times 1 dx. So the reason it's plus, it's minus a negative cosine, and I just combine the negatives. So step 3, put everything into the parts formula. And then step 4 is just evaluate the secondary integral. So I have this minus x cosine x. The integral of cosine is sine, so plus sine x, plus c, because we have now done our integral. If we want to check our answer, we just take what we think is the antiderivative and take the derivative of it to see if we get where we started. So the derivative of minus x cosine x with the product rule is going to be x sine x minus sine x. And we'll add sine x, that'll cancel out, and we'll be back at x sine x. So find the derivative of your answer using the product rule in this first term, and the derivative of sine is cosine. And then, oops. So derivative of sine is cosine, that cancels out one of the terms. And then step 5 would be repeat if necessary. Sometimes the secondary integral is also a parts integral. Sometimes the secondary integral is a substitution integral. But that's the process for integration by parts. You're given u and dv. You go find du and v, put it into the parts formula. The integral of u dv is uv minus the integral of v du. And then finally, evaluate the secondary integral. Earlier I said we had to decide on which factor is going to be u and which factor is going to be dv. And the question will be, how do we know which one goes where? The answer is, in the beginning, you don't. But you get it wrong a few times, and you start looking for patterns. I come up with one rule for this process, and that's that dv must be something that you can integrate. So when it comes to how to decide on u and dv, my one rule is that dv is something you can integrate just by looking at it. So my rule, dv must be something you can integrate. That's my one rule for how to decide which one is u and which one is dv. dv is something that you can integrate. The rest of the rules you have to discover on your own by making mistakes. I'm not going to tell you what to do because you have to figure it, because you won't know why. So I'm just going to leave it at that. dv has to be something that you can integrate. Any questions?
Yes, for facilitate, if you don't mind. On the very bottom, we have the step 3, very bottom. And on the top line, one line before that to the right, we have like a cosine x with dx. On that's the case, the cosine x is the v, correct? And the dx is the du, correct? Am I right?
Correct. Minus cosine x is the v, and the dx is the du.
Yes, the du, if I look on the left, that's equal 1x, am I right? On the top line.
Du is x. Sorry. Du is dx.
Yes, that's what I mean. Okay.
Yeah, 1 dx.
And then you take the integral on the very last step. Then we need to take that integral from the cosine x that become sine x plus c. Got it. Thank
Correct.
you.
Any questions? So it seems nice and straightforward, and everybody should have a nice positive feeling about integration by parts. This is because this is the first example, and we always pick the first example to give you a false sense of security. Oh, I mean, build confidence about your understanding of the process. So our project is going to be to look, this week is going to be look at integration by parts and see what we can do with integration by parts. Two of the most important rules. You start off by identifying that it's not that you're not looking at a substitution problem. That's step 0. And then step 1, you decide on u and dv. You get to decide how to break apart this integral. But you have to remember that dv is something that you're about to integrate. So the dv has to be something that you can integrate. After that, it's just a matter of putting parts into the formula and then evaluating your secondary integral. So here's what I mean by about not substitution in step 0. So for example, even though we just learned our fancy parts formula, if I gave you the integral of x times sine of x squared dx, we don't want to try to read this as a parts problem because this one stands out as a substitution problem. I see x squared inside of sine x. There's a composition of functions there. To make the substitution w equals x squared work, I need a copy of x to be the dw, and I have it. I have that x out in front. So this is not substitution, or sorry, this is not parts because we can make the substitution w equals x squared. That's inside the function sine x, which we know how to integrate. So we're going to be integrating sine of w. And that x outside the sine of x squared is just there to be the derivative of the inside. So the dw is 2x dx. And so we can write this as x dx, the factors that we have, as is a 1/2 dw. So now we're going to integrate. We're going to get this factor of 1/2 from the dw. The integral of sine of something is minus cosine of that thing. And in this case, that thing is x squared. And then we make sure to put a plus c at the end so we don't lose a billion points. Wasn't a parts problem, it was substitution all along because we had something that we could identify as the inside, and the x in front of the sign was something that could be the outside function. Let's pretend that we didn't see this was substitution. Let's suppose that our first protocol, checking for substitution first, failed. Now we're on to the second line of defense. So U is going to be, we'll just do this like last time. U is x, and I'll make dv equal to sine of x squared dx. And now we've run into a problem. This is not going to work as parts. Now we had a problem because we don't know what v is. We don't know what the antiderivative of sine of x squared is. We know the integral of x sine of x squared because we can do substitution, but we don't have the integral of sine x squared. That's the first indication that something has gone wrong. Or actually, that's the second one. We missed over the substitution. We didn't see the first thing that went wrong. So when we try to split it up with a u and a dv, we can see that this is not going to work because we don't know the integral of sine of x squared. So we're stopped from doing parts, at least this way. So just because this way we assign the parts didn't work, what if we assign the parts the other way? What if instead of x is u, what if I make u equal to sine of x squared? And then dv, which has to be something we can integrate, is just going to be x dx. Now, dv is something we can integrate. So at least at this point, it looks like things are working. After we assign u and dv, we find du and v. We differentiate u to find du. The derivative of sine of something is cosine of that thing times the derivative of that thing. The integral of x is a 1/2 x squared. Everything seems to be proceeding. I switched over so that dv is now something I can integrate. Now I just need to put things together into the parts formula. So the parts formula will have uv so 1/2 x squared times the sine of x squared. That's fine. Minus the integral of v times du. So I have a 1/2 x squared times a 2x cosine x squared. The x. We can clean this up a little bit. There's a 1/2 and a 2 that can cancel out, but we still need to evaluate the secondary integral, and now we are stuck again. So 1/2 x squared sine of x squared minus the integral of x cubed times the cosine of x squared. Now we might notice that this is x cubed cosine of x squared. This looks like worse than what we started with. We had x to the first times sine of x squared, and now I've got x to the third cosine of x squared. This looks worse than what we started with. The secondary integral is worse than what we started with. So this should be a big red flag that our process is going to lead us astray. Because once again, I can't just assign u and dv. dv can't be x cosine of x squared because we don't know what the integral of that is. Now we might look at this, and some of you might notice that we could do a substitution. If we were going to notice substitution now, then we would have noticed the substitution at the beginning. But wait, maybe we needed this time to pass. Notice that the substitution that we make here is the substitution that we should have made in the initial problem. So technically, we can use substitution on this secondary integral. But the substitution that we're making here, w equals x squared, is the substitution that we should have started with in the original problem. So even if you miss the substitution at the beginning, if you try parts, dv has to be something you can integrate, keeps you from trying to put sine of x squared over in the dv side, because we don't know the integral of sine of x squared. Assigning the parts the other way sometimes is the answer, but in this case, it's led us to an integral that's worse than what we started with. Another place you'd notice that you're not in a parts problem is when you're assigning dv, we don't know the integral of sine of x squared, but if there was an x there, we do know the integral of x sine of x squared. But in that case, we're not going to do parts. We're just going to drop back and do a substitution. So step 0, is this a substitution problem? If not, then step 1, assign your parts. Remember that dv has to be something that you can integrate. Any questions?
Yes, Professor Leach, just a quick question. On the example, it said, what if we try part? So the dv equals sine x squared dx. How come we cannot take the interval, the v?
We don't know that. We don't know what the antiderivative of sine of x squared is.
Oh, so we don't know, huh? Even
Yeah.
that.
It's not cosine of x squared because the derivative of cosine of x squared is cosine of x squared times 2x.
Okay, I will do more review on that. Thanks, Professor Leach.
Mm-hmm. All right. That's introduction to integration by parts. It's the anti-product rule. Remember that when you're learning a technique, the most important thing to do is something. You have to start doing stuff. You have to see that if you assign parts one way that you and you get stuck, you are not done trying that problem. Switch the parts. What if the parts are the other way around? Is there any other way that we can divide up these parts to make dv something I can integrate and my secondary integral a simpler integral? So it only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time. You have to know it so well, you have to know what you don't know. You have to know that you don't know what the integral of sine of x squared is. Some of you are thinking just divide by the 2x. Go ahead and try that. Take the derivative of what you get with the over the 2x part and see if you get the same thing back when you use the quotient rule. So that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.